Okay, sample problem 19.8. A current of 1.26 amperes is passed through an electrolytic cell containing a dilute sulfuric acid solution for 7.44 hours. Write the half cell reactions and calculate the volumes of gases produced at STP. Okay, so it's an interesting problem. They're saying it's just dilute sulfuric acid. So you're like, what's going on? Where's sulfuric acid? This is from the lecture. It's the issue of dilute sulfuric acid is often added to water to promote the electrolysis of water. Okay? So the idea here is that when you're looking at the electrolysis of water, what happens is you're going to produce two gases. You're going to produce hydrogen gas and oxygen gas. So what you do, if you want to, is you can go to the table 19.1 and look up the production of hydrogen gas and oxygen gas, and you'll find them there. Okay, so here's what happens in the anode for the electrolysis of water. Water produces oxygen gas plus 4 hydrogen ions plus 4 electrons. That occurs at the anode. That's the oxidation. And then at the cathode, what happens is the reduction of hydrogen ions. So 4H plus 4 electrons to give you 2H2. Okay? The overall reaction for the electrolysis of water is 2 waters produce oxygen gas plus 2 hydrogen gas. It's the reverse of the formation of water, essentially. Okay? Non-spontaneous reaction. So we would apply a voltage that overcomes the non-spontaneity of this reaction in order to move it forward. So let's go through the calculation. There's 2 gases that we're going to have to calculate for. So what I'm going to do is I'm going to go and do oxygen first, then we'll come back and do hydrogen. Okay? Step 1, the amount of electrical charge is equal to the current times the time. The current is given as 1.26 amperes, which is coulombs per second, times the time, which is 7.44 hours, but we need to have it in seconds. So I'll just do it in one step, 3,600 seconds per hour. And that will give us coulombs. We're trying to find the amount of charge. So 1.26 times 7.44 times 3,600. And that gives us 33,748. So 33,748. Coulombs. Now we're going to do oxygen first. So it's 1 mole of oxygen for every 4 moles of electrons. But we don't have moles, we have coulombs. So we're going to convert this to moles. So 33,748 coulombs. Faraday's constant. We divide by Faraday's constant. 1 mole of electrons is 96,485 coulombs. That's a C for coulombs. This is an E negative for electrons. So we're going to take our coulombs that we just calculated and divide that by a Faraday. So divided by 96,485, and you get 0.3498. 0.3498. Now we're in moles of electrons. Now we can use this relationship here. It's 1 to 4. So 0.3498 moles of electrons, and it's 1 mole of oxygen for every 4 moles of electrons. So you need a lot of electrical current to produce oxygen gas here. So we're going to divide it by 4s. and you get 0.08744. Now it tells us this is at STP, so we use the ideal gas law. We're trying to find the volume, right? It says find the volume. We already have the half reaction, but find the volume. nRT over P. Okay, so 0.08744 moles. The gas constant is 0.08206 atmosphere liters per k mole. Temperature is STP, so 273 Kelvin. And then luckily this is 1 atmosphere because it's STP. So if you go through the dimensional analysis, you'll get that it's in liters. So just multiply it by RT. So times 0.08206 times 273, and you get 1.96 liters. Now, if you're clever about this, you can do the hydrogen very easily, and here's why. Take a look at what happens in these two reactions. 4 moles of electrons gives you 1 mole of oxygen gas. 4 moles of electrons here gives you 2 moles of hydrogen gas. So since these two numbers here are the same, and this number gave us 1.96 liters of oxygen, that number should give us twice as much hydrogen. It should be a 2-to-1 ratio. Okay? So if you want to go through it, you can. You can say, look, we've got 0.3498 moles of electrons. We calculated that up here. And then it's 2 moles of hydrogen for every 4 moles of electrons. Right? And so what does that do? It gives you, let's try it, 3498 times 2 over 4. .1749. Right? And then you can, again, use the ideal gas law, nRT over P. So it's 0.1749 times 0.08206. It's at STP, so 273 divided by 1 atmosphere, right? But look at this number here. This number here is just twice what that is. So you're going to get twice the volume. But you could run it through, and you'll get it. It comes out to about 3.92, right? 0.1749 times 0.08206 times 273, and you get twice as much. So there you go. Okay? If we had been asked to find the mass of these materials, then instead of using the ideal gas law, we would have taken the number of moles and multiplied that by the molar mass to get the number of grams. We would have taken this number of moles here, multiply it by the molar mass of hydrogen to get the number of grams of hydrogen. That's also a common type of calculation. Okay? So there we go.